こんにちはクラスの皆さん。また、木講義へようこそ。今日は、複利という金融のテーマを取り上げます。あれ Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling the finance topic of compound interest. To introduce this, we're actually going to revisit simple interest here for a second, and here's the formula for simple interest. You've got an amount equal to some principal amount multiplied by 1 plus some rate, right? Some APR divided by how often that rate is broken up, multiplied by some amount of time. So for simple interest is always calculated based on this principal amount only. The only thing that this amount is multiplied by is this 1 plus rate over n times t sort of situation. Interest is usually just a one-time calculation. You can calculate it more than one time, but let's say you're trying to find, maybe you have an APR of 10%, right? And you want to find out how much you have after like 30 years. So this would be, 0.1. Probably the whole thing would just be 0.1. You wouldn't even break it up in that sense. And then your t would just be 10 because it's going on for 10 years. But then you only multiply by the principal amount the one time. The way that compound interest works is that interest is always calculated based on some kind of current or running amount in your balance. So the principal is actually only used one time in the kind of very first interest calculation. And then after that, it's whatever's in the account or whatever's on the balance that is used to calculate interest after that. So usually it's calculated at a set intervals of time that are within a year. So maybe interest is compounded monthly, or maybe it's compounded daily, or semi-annually, or biannually, which confusingly I think are the exact same thing. Don't quote me on that though. So on and so forth, right? So the question is, what is the formula that we should use for compound interest? Because at its core, you're accruing interest off of interest that has already been calculated. That's what compound interest kind of means. It's interest on top of interest, essentially. So here's the main idea. Suppose we have an APR of 6% and a principal amount of $1,000. Okay, we want to have the interest broken into quarters, which actually for simple interest doesn't really mean a whole lot unless we were doing it at some non-whole number amount of years. But we want to know how much we would have after 2 years. From a simple interest perspective, you just run this through the formula, right? You do 1,000 times 1 plus really 0.06 times 2. This is kind of just for show at this point. Like, we don't need to break APR up into 4 different pieces, even though it's, being broken up into quarters. But then you're multiplying it by how many quarters, go by. There's 8 quarters in 2 years, and so we're multiplying by 8. But really, 8 divided by 4 is just 2. You could just write this as 1 plus 0.06 times 2. Oh my gosh, my handwriting is atrocious when I'm trying to write like this. No matter what, you're going to end up with this amount, $1,120. Now, if we want to do this for compound interest, the broken into quarters part of this sentence here is typically written as something that's compounded quarterly. Meaning, just like we did before, you take the 6%, you divide it into 4 pieces, and every quarter in a year is accruing 1.5% interest. That's how the APR can be 6%. I mean, again, we did the same thing here, but we didn't have to actually write it like that. We could have done 0.06 times 2. That'd actually be the same thing as 0.015 times 8. Okay, but back to here. If I wanted to calculate the amount after the first quarter, so this is amount sub quarter 1, right? What we would do is we would take 1,000, you'd multiply it by 1 plus 0.015, and you get this amount. Okay, so actually right now, it's not really any different than a simple interest. But here's how it's different. In quarter 2, you now use the amount that was there from quarter 1, and then you apply 1.5% interest onto it. So now you're at 1030 with some change. Right, in quarter 3, you're using that 1030 and change to find 0.015 or 1.5% of it to get 1045 and some change. Then after 4 quarters, right, you take the 1045 and some change and you find 1.5% of that and add that to the account. So at the end of 1 year, we're at 1061 and some change. We keep doing this, right? That's only 4 quarters, which means only 1 year. We're trying to do this in 2 years. So here's the calculation for doing all of that stuff. And the thing to notice is that every quarter you're using what's currently in the account. right, from the previous quarter to figure out what that amount is. That's essentially how compound interest is different than simple interest. You're finding an interest based on a current running total that's in your account or on your balance or whatever it is that you're working with. So you'll notice that at the end of everything, we got $1126.49. So we got an extra $6.49 approximately. And all of that can be attributed to, well, we're finding interest on top of interest, right? That's why our account has a little bit more in it at the end of 2 years than if it was just a simple interest calculation. So you can imagine that, maybe if your percentage was higher or if we invested a little bit more money, the difference would start to get staggeringly high, right? Like the difference between these two numbers is what I'm talking about. Compound interest can garner significantly more interest than just a simple interest calculation over time. Okay, now as far as coming up with a formula for this goes, because that's the whole thing we're trying to do is what's the formula for compound interest? The thing that's to notice, and there is a trick for this, but I don't think I'm going to explain it in super detail at all. But essentially it's realizing that the number that you found here was found from this previous entire calculation. This number was then found from this previous calculation. This number was found from this previous calculation. And we'd have to go back all the way to quarter one to see that this 1.015 shows up 8 different times. And that's what's being multiplied by your principal, right? Principal was 1,000 originally. And this times 1 plus 0.015 thing would be repeated 8 different times. There'd be 8 instances of this thing right here. And so you can consolidate it like this. 1,000 times 1 plus 0.015 raised to the 8th power. The 0.015 is the APR divided into quarters. And the 8 is 2 years multiplied by quarters, right? There's 8 quarters in totality in 2 years. And that gives birth to this formula, the compound interest formula, which says P sub n is equal to P sub 0 multiplied by 1 plus r over k raised to the nk. But what does all this stuff mean? Well, P sub n, that's the amount after n years. So n represents a number of years. P sub 0 is the same as it was for simple interest, so it's our principal amount. K is how many times the interest is compounded per year. So quarterly meant that we used 4. It could be monthly, in which case you'd use 12. It could be yearly, in which case K would be 1. Maybe it's daily, in which case it's 365. R is your APR, your rate as a decimal. So if it's like 5% interest, annual interest rate, AIR sometimes is another acronym for APR, then you'd use 0.05. All right, so that's the formula. Let's look at some examples. All right, example number 1. Suppose Ben invests $2,175 into an account with an APR of 7% interest that's compounded monthly. How much will he have in 10 years? So here's our formula. And essentially what I like to do now is I like to go through the sentence structure and figure out what do we know. The first thing I like to do maybe is actually what am I trying to figure out? We're trying to figure out how much we will have in 10 years. So this is the unknown. So all of this other information is given somewhere in the paragraph itself. So let's find that. First, we know the principal. It's $2,175. That's how much Ben is investing into this account. Next, we know that the rate is 7%. So it's 0.07 and it's compounded monthly and there's 12 months in a year. So this 7% interest rate is going to be broken up into 12 equal pieces throughout the year. And at every one of those intervals, right, we're calculating what the interest accrued is. We're calculating what the new balance is. Finally, we know that we're doing this for 10 years. So we use 12 times 10, right? I guess based on the formula, I should have written it the other way. I should have written it as 10 times 12 because it's nk instead of kn. But you know what? Multiplication is commutative, which means order doesn't matter for multiplication. Anyway, this is all equal to P of 10, P sub 10, because this is the amount after 10 years. So you run all this through a calculator. I like to use Desmos, and you come out to something that is approximately $4,371.01. And that's it. That's all you got to do. Here's another one. Miss Plum wants to buy a car, and she wants to do this in 5 years. She knows the car is $27,000 and that typical interest rates on savings accounts are something like 1.3% compounded daily. How much will she need to invest so that she can afford this car in 5 years. So the thing that we don't actually know here is P sub 0. That's going to be our unknown in this example because we don't know how much Miss Plum wants to invest. But we do know like this, for example, right? The car costs $27,000. That's the goal for this. So what we're trying to figure out in this one is how much should be invested to get $27,000 given that we only have a 5-year time frame. Okay, so we know that $27,000 is the goal. So we're going to set that equal to P sub 0, the principal that we're trying to find, times 1 plus the rate, which is 0.013 as a decimal, divided by, now K, in this example, is 365 because we're compounding it daily. So then we'd raise that to the 5 times 365 because we're doing this for 5 years. Now in this one, we can't just calculate everything. We're going to have to solve for P sub 0. But here's the thing, P sub 0 right now is being multiplied by this thing. So we just need to divide both sides by the thing that I have in the box. And that would cancel it. So all this stuff goes away. And our answer would just be 27,000 divided by this mess of stuff that we just divided by. Right? So we have this, which again, I just used a calculator to get this. Now, I know plenty of students who don't like to put stuff in a calculator like this. In fact, like if you're using an iPhone, you shouldn't do this, right? If you're using some kind of phone or handheld device, you probably don't want to do this. You know what though? Technically, isn't a graphing calculator a handheld device? In which case you probably do want to put it in like that. But anyway, my point is, if you're not using Desmos, maybe you want to actually calculate like what this number is. Like approximately. You probably want to be pretty accurate when you are rounding, like go to the nearest like 7th significant figure. But then you could just do 27,000 divided by whatever that number is. I'm super lazy and I just plug everything in kind of as is into Desmos. And so that's what I did here. And I got that she basically needs to buy the car. She saves like, what even is that? $1,700 about by waiting 5 years. So probably not worth just opening up a savings account to do this sort of thing. But there you go. Now we know why, right? Because the interest rates are way too low on them, usually is the reason why. The last one, example number 3. Suppose that Holly earns a salary of $70,000, but every year she gets a 2.5% cost of living raise. So every year her salary increases by 2.5%. In how many years will the salary eclipse 90,000? Okay, so Holly wants to know, just based on cost of living raises, when will her salary be 90,000? Okay, well that's what we're trying to find in this one. We're trying to find N. How many years is it going to take for us to get to here? So we plug in all of this stuff, and we get this. 90,000 is equal to 70,000 times 1 plus 0.025 over 1, because we're just, it's kind of, I didn't say how the APR was compounded, but she gets this raise every year. So we're going to say it's compounded annually. Actually, one of the reasons I like this question is because it's not related to like a savings account. It's just based on salary. But you can still use the compound interest formula to figure out, when you'd reach a salary of something. If you knew that you got like scheduled raises every year or something like that. Now, you might be wondering, how in the heck do we solve for a variable when it's in the exponent position? You can't just divide by all this nonsense and then get n by itself. N is an exponent for the nonsense, right? So how the heck are we supposed to solve for it? Logarithms. Now, this is not a pre-calculus class, okay? So I'm not about to teach you logarithms in general. Like, essentially, they're a function, they have their own domain, like, you can graph them, they're the inverse of exponential functions, and, like, there's all these properties that go into them. We're just going to use one thing about logarithms. And in this class, in Math and Society, you only need to know how to do this one thing with a logarithm. To introduce how that works, let's look at some really basic equations, right? If I have x plus 10 is equal to 100, and I want to solve for x, what I have to do is I need to subtract 10 from both sides, and I'm done. The reason you subtract 10 is because subtraction is the inverse operation of addition. If I have 10 times x is equal to 100, and I want to solve for x, I need to divide by 10 because division is the inverse operation of multiplication. Similar still, if I have like x squared is equal to 100 and I want to get x by itself, I square root, because square rooting is the inverse operation of squaring something. Well, the same sort of thing happens here. If I have 10 and it's raised to the x power, and what I'm trying to do is I'm trying to solve for x, you have to apply the inverse of a base 10 exponential to both sides, which happens to be what the logarithm function is. The way that we denote it is we say log, and then in parentheses we put the thing we're taking the log of. But the whole point of doing this is so that we can use this logarithmic property that says when you have the log of something, right? When you have the log of, we'll call it a raised to some power, like x, that's the same thing as x multiplied by the log of a. So what basically happens is you're allowed to bring the power, which in this example is x, down in front of the logarithm. So now it's just x times the log of 10, and it's equal to the log of 100. Now, remember, the log is a function. It's no different than like a square root. I mean, that's a lie. It's very different, but it's this similar type of thing, right? A square root is a function, right? The square root of 10 can be calculated. Well, very similarly, the log of 10 can be calculated. It's an actual number, okay? And again, we're not going to get into, well, how do you define what that log is? That's for a pre-calculus class. But if you now divide x log 10 by the log of 10, then those things cancel and you just get to plug in to your calculator log of 100 divided by the log of 10. So that's the idea. Let's say that we have 250 is equal to 4 times 7 to the x. Okay, I just made this thing up. Couple things to keep in mind. No, you can't make this 28 to the x. By order of operations, 7 needs to be raised to the x first, and then you multiply by 4. Okay, so it's just, it looks weird, but this is an equation. 4 times 7 raised to the x. First thing you need to do is you need to get to 7 to the x by itself. So I'm going to divide both sides by 4. Now I have 62.5 is equal to 7 to the x. I'm going to take a log of both sides. Log of 62.5 is now equal to the log of 7 to the x, so that I can use that log property to bring the x down in front of the log of 7. Once I've done that, it's just x times the log of 7. The log of 7 is a number, right? We don't know what it is, but it's a number. It's x times something. So to undo it, you just divide by the log of 7, you plug that into your calculator, and so in this particular case, we get that x is about 2.125. So again, the main idea is if you have the log of some stuff that's raised to the x power, that's the same as x times the log of some stuff. There is actually an explanation for why this works. We're just not going to get into it in this class. But we still need to use a logarithm to solve for something like what we're trying to do. Something like this, right? So here's what we're going to do. We're going to isolate the stuff that's being raised to our variable, right? Here's the stuff. Isolate all this stuff that's being raised to the n, which means I should first divide by 70,000. If I want to be fancy, I could actually just write this as 9/7, because 90,000 divided by 70,000 is just 9/7. But I didn't do that. I'm being extra lazy. I'm being as lazy as possible here. But now I have the stuff. Oh, one thing I did do is I turned 0.025 divided by 1 into 0.025 and n times 1 into just n. So keep that in mind. But then now I have it isolated. I have the stuff raised to the power isolated, so I'm going to take a log of both sides. And all that is writing log in front of both sides of my equation here. Because this log exists, I can use the log property that says, hey, bring down the exponent in front of all that stuff. So I did that. Now I have n times the log of 1 plus 0.025, which is a number. So I'm going to divide both sides by that particular number to get n by itself. And then according to Desmos, we get 10.17 years. But since Holly only gets these raises every year, she can't get it in the middle of a year. So at the 11th year, she'd be past 90,000. All right, so that's it. Logarithms are a little weird, especially when you don't know what it is, really. And honestly, if you're interested to know more about logarithms, I have a video on them. So you could look that up in my channel. But that's it for this one. That's compound interest and the different types of things that you could solve for in different situations. So hopefully you all enjoyed. Hopefully you learned something. If you have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.